Welcome back to Learning with Ms. H. Today we're going to go through the tools of astronomy and take a look at light and telescopes. Your bell work for today is actually for points, so please make sure you do this. Bell work assignment. Read the following questions and type your answers in the text box below. You have unlimited attempts on this, so you should be able to do this as many times as you need to. What are the units of measurement? What unit of measurement would you use to measure the distance between Earth and Neptune? Remember that this is within the solar system, so what unit do you use for that? And then what are some countries and cultures that developed early astronomy? So answer both of those questions down here in the text box. You can just type number 1, number 2, and then come down here to submit and turn that in. The bulk of the lesson today is going to be spent going through this presentation. You're going to read through these slides, take notes over these in your notebook or Google Doc, wherever you're taking notes at, and then complete the homework assignment at the bottom. So let's go through the homework first so that those of you who want to do the notes on your own can go ahead and turn off the video. So Tools of Astronomy homework. This is going to be a quiz. It's not really a quiz, it's homework worksheet type thing. Remember that we had to do the quiz setup in order to get the worksheets in here. So, you are going to go ahead and click Take the Quiz. And you're going to answer these questions. Some of them are drop downs. On these that are multiple points, you will have to get each one of these correct to get your 4 points. So when you get your score back, it's going to show you which answers you got wrong. You're going to have to come in and redo the entire quiz to make sure that you get all 4 of these right to get your 4 points. Same thing here. You will need to redo this until you get all of them right in order to get the 4 points. As of our last check on this, if you miss one of these, you miss the whole 4 points. That is supposed to be getting fixed. That is a Canvas thing, not a setup thing. So please make sure that if you don't score 100%, you come back in and you retake it and you fix what you missed and answer all of these. That way you can get all of your points. Once you're done, click Submit Quiz, and you're done for the day. So let's come in here and do the PowerPoint for Tools of Astronomy. It's not super long, but there's quite a bit of information in here. So go ahead and pause the video, grab whatever it is that you write with and on, and then come back and restart the video. All right, welcome back. We're going to talk about tools of astronomy today. The first thing we're going to talk about is light. We use light to be able to view things in the night sky. Our telescopes actually gather light. It needs to be super dark to use them, but they gather light from the object you're trying to view, and that's how it shows up. So if you have a lot of light around you, it's not going to be able to focus on that faraway object, and it's not going to work. So we're going to talk about each of these parts of light: electromagnetic spectrum, wavelength, and frequency. You're going to have a lot here you're going to need to write down. So this image on the right is guaranteed to be on the test. You will need to be able to understand this image and list out where things fall on the electromagnetic spectrum. Gamma rays are at the 10 to the negative 6. Radio waves are down here near 100 kilometers. So you need to know the order of these, and you need to be able to recognize it, whether it's top to bottom or left to right. I think the one on the test is actually left to right. So gamma rays would be on the left at 10 to the negative 6, radio waves on the right at 100. So make sure that you remember the order and you remember the end that each of these are on. You also need to know the order of the colors. That visible light is only a very small section of the electromagnetic spectrum here. And we have violet is the shortest, that's purple. Red is the longest. So it may ask you which is shortest or longest. You need to remember that violet is shortest, red is the longest. So what's the electromagnetic spectrum for? Well, all light is emitted as electromagnetic radiation, and the spectrum measures that radiation. Light moves as a wave. It does have particle-type properties, but it mostly moves as a wave. Again, visible light is only a small portion, and then electromagnetic radiation includes a large spectrum, and these are all of the pieces that are labeled on this image. Wave, moving as a wave versus moving as a particle. We're not going to get super deep into this. That's getting into more physics type things. But waves kind of move through the air. Think of like radio waves that are emitted from cell towers, microwaves that are emitted from your microwave. They move through the air, and they can move through things. They can move through objects. They're not really solid. Light, on the other hand, is a little bit more like a particle because it can bump into things and it gets stopped by things. When you have a room light on and you close the door and go into another room, you don't see the light coming through the door. You only see it through the gap underneath. So even though light moves as a wave, it is stopped by solid objects like a particle. Again, remember, anytime you're doing notes with me, you can go ahead and pause the video anytime you need to catch up and finish writing. I don't want these to be an hour long, so I'm going to go ahead and move through them at a faster pace and trust that you will pause, finish writing, and restart it as needed. So wavelength and frequency. These are two terms you have to understand. Wavelength is the distance between two peaks of adjacent waves. So at the top here, you can see this blue line with these really close together waveforms. So this squiggly line is a waveform. When they're close together at the peak, that's a short wavelength. Down here at the bottom where they're much more spread out, it's a much wider loop. That's a long wavelength. And you always measure the wavelength at the top of two adjacent peaks. Frequency is the number of waves that pass a given point in a given amount of time. So if this was over, say, 1 minute of time, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 peaks on top, and you have 4 peaks on bottom. So wavelength is how close together they are. Frequency is how many of them pass through in a given time. So these wider waveforms have a lower frequency because you have fewer of them there. So if you measure wavelength, you go peak to peak. To measure frequency, you would go end to end during that time period. So frequency of 4 and a wavelength of whatever this distance is in between here. 1, 2, 30 millimeters or something like that. So fairly close to that on my computer screen. If you put this up on an overhead projector, it may actually look longer. But you would measure from peak to peak for the wavelength, from end to end for the frequency. Here's a closer or larger picture of that. I would put this in your notes. You will probably see this on the test. So we have different types of radiation in the electromagnetic spectrum, And the different types of radiation are going to have different wavelengths. Radio waves are going to be measured in kilometers because they travel really long distances. Gamma rays travel short distances, and they're going to be measured in billionths of centimeters. And I put an example of what that would look like in decimal form down here. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 zeros in front of the 1. So a billionth of a centimeter. Shorter wavelengths are going to have higher frequencies because you can fit more of them into a given time frame. They have more energy. You have to have that more energy to keep them going at that faster rate. Longer wavelengths are going to be lower frequencies because they pass, fewer waves will pass by the given point in that same time, and so they're less energetic. It doesn't take nearly as much energy to keep those longer wavelengths going. Visible light is considered white light. That's the light that we see. It consists of all the colors of the rainbow. Remember that red has the longest wavelength. So it has less energy. Violet or purple has the shortest wavelength, and it has the most energy. So remember, more energy, short wavelength, higher frequency, so that is our purple. And then the longer wavelength with lower frequency and less energy, that's our red. And this is showing you an image of a prism as the white light enters. And then you can see that as the light passes through the material in the prism, it passes through at different speeds, so it separates out all of the different colors. Telescopes. We're going to be talking about several different types of telescopes, but the telescope is the main tool of astronomy. It's what we use to view the night sky. So, features of a telescope. You have a lens, which is the objective lens where you're looking in. They are going to bend and refract light to produce an image. So the light comes in on the end of the telescope here. It travels down the tube. It converges at a focus. That's this point down here. And then it's going to bend up to your eyepiece where you're going to view it from. The distance between the lens and the focus is the focal length. So the distance between the lens here and the focus down here is your focal length. This is in a refracting telescope. Refracting means it bends the light. And these are the most inexpensive, so they're the more affordable telescopes to get. This is what most of the telescopes that you can get at places like Walmart, Target are going to be. The next type is a reflecting telescope. These are more for hobbyists, people that are a little bit more serious about stargazing or have a little bit more money to spend on it. They are more expensive because they reflect light off of a mirror to focus the image instead of refracting it through the lens. So instead of having that focal point and the refraction going on, they have a flat mirror that's back here. So the light comes in, it travels down the tube, it reflects off the primary mirror, which has a curve to it, up onto a secondary mirror that is flat, and then up to the eyepiece. So on these, it comes in, it gets mirrored, so it's flipped backwards, then it gets mirrored again, so it's flipped right side, and then it comes up. On the refracting, it only gets flipped once. So you're getting a more true picture in the reflecting telescope. You'll see that they are generally much larger. They gather a lot more light, so you can see a lot further, a lot more clearly. The only issue with these is what's called chromatic aberration. An aberration is an anomaly or a difference. So it can sometimes mess with the colors, so you don't necessarily get a true color picture of it. Um, they might be off a little bit. This is, however, what most research telescopes use today. They're built this way with the reflecting telescope. These can be massive. There are research telescopes out there that are gigantic, tens, if not hundreds, well, several tens of feet wide. The main observatories have gigantic reflecting telescopes that they look through. These are a couple images of some larger telescopes. They can be Earth or space-based. So the space-based Hubble Telescope, it's got the lens cover out here that will cover up the area that collects the light. This is the tube it goes down. There's a giant mirror under here that reflects it back, a smaller one here, back again. So Hubble Telescope is out in space. It is able to collect a lot of light because in space there's not any light around it really, so it can see very far distances. You get less interference from light and atmosphere, but they're super expensive to build because you have to build them to last, and they're hard to maintain. So the issue with maintenance also increases the cost of the build because you can't just walk over to it, see what's wrong with it, go back and build a part, and then go back again to replace it. These are going to be things that would have to be replaced from space. Earth-based telescopes are a lot easier to maintain because that can be done here on the ground. They're in these bubbles at this laboratory, this observatory. You can go inside. This is the building down here, and this is the part that houses the telescope. This ceiling will retract and open up so that the telescope can be seen, can view out the top and be moved around. It changes angle, position, so it can look at different parts of the sky. And these buildings are the ones that house the huge mega telescopes. The issue with Earth-based telescopes is they can get a lot of interference. You have light interference if you're near any kind of civilization at all. So most of these observatories are off on their own, kind of in the middle of nowhere. And you'll often find them high on mountaintops because of atmospheric interference. If the atmosphere is thick or unstable, it can actually cause the images you get back to be blurry or wavy. So you want a very clear, smooth, stable atmosphere. And the higher up you go, the more stable the atmosphere is. So you'll find these big observatories at the top of mountains. Seeing what can't be seen. There are other types of telescopes that will see parts of the electromagnetic spectrum that we cannot see with the naked eye. One example is a radio telescope. It looks like a satellite dish, and it's built to gather gamma rays, radio waves, those kinds of things. Things we can't see with the naked eye. So it collects that data. The good thing about this, it does not need a smooth atmosphere. It doesn't need a perfectly smooth surface to be collecting, and they really do look like giant satellite dishes. The problem is you get very poor resolution with this. The fact that you don't need all of the smoothness, when you get the data back, it's very, think about like a picture that's pixelated badly, and that's kind of how the data looks. It's very snow on the TV-ish. You need a lot of data from a lot of these radio telescopes to determine a position of something. So you'll need a lot of these in different locations, measuring angles and distances, and kind of triangulate all of that, put it together to determine a position of whatever object you're looking at from multiple collection sites. These can be used 24/7. You don't have to have a person running this. Most other types of telescopes, you're going to have a person running it, or at least telling it, here's your program, run this program, and then coming back to check on it. The other good thing about these is they can see through space dust. If we have clouds of space dust floating around, a regular telescope is going to be blocked by that, because remember that light doesn't travel through particles, through solid objects. So if you have a cloud of dust, it's going to block out a lot of that light. The radio telescope doesn't have that issue. One big array of these is the Seti Array. It's out in the desert in the western United States. It's been around since the 80s, if not the 70s. They're out there searching for alien life. So that's it for the notes. Go ahead and work on the homework. Make sure you've turned in both the bell work and the homework, and you are done for the day.